All right, hey guys, I thought I'd just make a video and go over the solutions to the study guide here. So I won't be going super in depth because most of this is fairly self-explanatory, and I will focus mostly on the concepts since basically all of the problems, with a few exceptions, are just algebraic manipulations of equations that are given to you. So starting off here, our first question says the equivalent capacitance of a group of capacitors in series, and it should say is always less than the capacitance. So capacitors work the opposite way that resistors do. Whenever you put them in series, the equivalent capacitance has this inverse of the inverse nature. And so the resulting equivalent capacitance is less than any of the individual ones. Whereas if you put them in parallel, it's greater. The equivalent capacitance for capacitors in parallel is just the sum of all of the individual capacitances. All right, now if you put a dielectric between the plates of a capacitor, the capacitance increases, but the energy decreases. So that's just going down to this question here. That's because whenever you put a dielectric between the plates of a capacitor, the atoms in the dielectric create an electric field that opposes the electric field of the capacitor itself. So both the electric field is weaker and the amount of energy that's saved in the capacitor is less. Okay. A farad just is a coulomb per volt. Okay, and so this, you might would have been tempted to say true for this, because the capacitors that we looked at the most were parallel plate capacitors, which is what's described in this question, two plates that are separated by some distance that are parallel to each other. But that's only one type of capacitor. We also have spherical capacitors, where we have these spherical shells, one inside of the other, where there's charge on each part of the sphere. That's also a capacitor. We also could have these cylindrical ones that we look at. A capacitor store energy, that's true. The energy is stored in the electric field between the plates, regardless of the type of capacitor it is. All right, so pretty much all of these short answer are just using the equations. So the only thing you'll have to know is which equation goes with which. So this equation here, the capacitance is epsilon naught times the area divided by the distance. This is for parallel plate capacitors. This one here is for cylindrical capacitors. And we know that because this is a capacitance per length. You can remember that log always is going to go with a cylinder. And then finally, this equation, 4 pi epsilon naught times the radii divided by the difference of the radii. This is for spheres. So that's pretty much the only thing you'll have to remember. And then this equation, the capacitance is charge divided by the voltage. This is always true. In fact, this is the very definition of capacitance. This is how we defined it. And so this equation will be true for every single capacitor. Now, number 3 here talks about a dielectric. So remember, whenever we put a dielectric between the plates, different quantities are changed in different ways. So the capacitance increases. This C naught, this is the capacitance if we had a vacuum. And we multiply by the dielectric constant. So this depends on what material that we put between the plates. And this number is always larger than 1 for anything that's not a vacuum, and it's 1 for a vacuum. So if we multiply the vacuum capacitance by some number greater than 1, it increases. For voltage, we divide the vacuum voltage by this number that's greater than 1, which means that the voltage decreases. And the same thing for the energy that's stored in our capacitor here. Now, charge is different though. Charge stays the same. So it doesn't matter what you put between the plates, the amount of charge on each plate is going to stay the same. Okay, now this is sort of the only real question that I could ask you from this chapter. And it's, what do you do with capacitors that are in a circuit if you have them in combination? So we know the rules for capacitors in parallel, and we know the rules for capacitors in series. And what do we do if we have some capacitors that are neither in series nor in parallel? So if we look at what I've labeled here C1 and what I've labeled here C2, these are neither in parallel nor in series. So what we do is we just look at some subset of the circuit here and say, okay, all of these are in series or all of these are in parallel. So C2 and C3 here are in parallel, which means that we can replace them with what I called C23. Now for capacitors in parallel, the resulting or the equivalent capacitance is just the sum. So we just add those two capacitances together, and then we replace these two with a single one. So we should always redraw our circuit here the way that I have. So I replaced C2 and C3. These were on their own little pieces of this circuit here. But when I replace them, I don't want to leave part of the circuit with no components in it. So the easiest way to do that is just to replace it with a single one here that's on the main part of our circuit. Okay, now all of these are clearly in series. So remember, to be in series, it means there's no junction between the wires here. So all of the current can actually go through the capacitors, but all of the current that's going through here has to go through here, it has to go through here, it has to go through here, because there's nowhere else for it to go. So all of these are in series. So we can replace them all with a single one. For capacitors in series, this is the rule that we use. We add up all of the inverses and we take the inverse of that. So we redraw the circuit one more time and we only have one equivalent capacitor now. Okay. Now the question also asks for us to find the voltage across each capacitor and the charge on each plate. Okay. So the way we do this is we look at our last circuit and then we just work backward. Well, there's only one capacitor in the battery in this circuit. And because of Kirchhoff's law, the loop law or the loop rule, the voltages across a closed loop have to sum to be 0. But we don't care about the sign of the voltage, just its value. So the voltage of this capacitor has to be the same as the battery because it's the only other thing in the circuit. So now that we know what the voltage is, we can use the definition of capacitance to find the charge. So capacitance is always charge over voltage, which means that charge is our voltage times our capacitance. So really we just multiply our value for the capacitance that we have times the voltage that we found, which was the same as the battery. And that gives us this charge. Okay, but I don't really care about this capacitor. I care about the ones in my original problem. So I just work backward. So this equivalent capacitance was found from all of these capacitors, which are in series. Now, since they're in series, that means they all have the same charge and they have the same charge as the equivalent capacitance. So we can instantly find the charge across all of these. It's the same as the one that we found above. And then I can find the voltage for each one, again, using the definition of the capacitance. Capacitance is charge over voltage. The voltage is charge over capacitance. So these all will have different voltages, but the same charge. Okay, now we're almost done. The problem is that C23 here is not one of our original capacitors. C23 came from C2 and C3, which were in parallel. So the fact that they're in parallel means that they have to have the same voltage. Okay, yeah, sorry, here we are. Because they're in parallel, they have to have the same voltage. Because there's a closed loop that only has those two through it. This is true for any capacitors or resistors in parallel. They have to have the same voltage because there's a closed loop that only has those two through it. All right, so we automatically know what the voltage is, and that voltage is the same as the voltage across the equivalent capacitor, which replaced them. So we know these voltages, which means that we can find the charge on each, once again, using the definition of capacitance. Now, one thing that you can do to make sure that you're right is if you have resistors in series, if you add all their voltages together, you should get the same as the equivalent voltage across the capacitor that replaced them. Similarly, if we have resistors in parallel, the sum of their charges should be the charge of whatever capacitor replaced them. Okay. Now this chapter is really easy. It's extremely straightforward. Let's go over these. Conventional current is defined as the direction that positive charges move. Any charged particle can be a carrier of current. So in real metals that we actually use as conductors, it's almost always electrons. But in general, you could have any charged particle carrying the current. Okay, now resistivity of a substance doesn't depend on the amount of the substance. That's true. Resistivity is an inherent quantity. It only depends on the type of the substance that you have, and then also the pressure that is under, the temperature and whatnot. But resistance is different. Resistance does depend on how much you have. So for instance, you don't just have to know that it's copper. You also have to know how much of the copper that you have. How long is the wire? What's the area, et cetera, that kind of stuff. Okay, now in a typical conductor, all electrons travel at the drift speed. That is not true. The electrons are bouncing around seemingly randomly. Only on average, over long time spans, can you see that on average, they're drifting in one direction at some speed. Okay, now resistance does change with temperature. Okay, not all substances obey Ohm's law. Ohm's law, remember, was just something that someone thought worked. It's something that he measured and found that does work, but you can't derive it. In other words, it's empirical. You just found it from observation. And so for some substances, it works. Some substances, it doesn't work. So for those that it does work for, they're called ohmic. And if it doesn't work, they're called non-ohmic. Okay, as temperature increases, resistivity always increases. That is not true. It depends on what the sign of the temperature coefficient of resistivity is. In particular, for semiconductors, alpha is negative, which means as the temperature increases, the resistivity and the resistance actually decrease. So they're better conductors as the temperature increases, which is atypical for normal conductors and insulators. The resistance and the resistivity increase as temperature increases. Okay, as electrons propagate around a wire, they gain more energy as they go around. This is not true. Any energy that the electrons gain by going across the battery, they lose by hitting all the atoms that construct the wire or in a resistor or something. From collisions, they lose any energy they gain. So we know that because as they go around the circuit, they travel at the same drift speed, right? The velocity is not increasing more and more as they go around, it stays a constant. Okay. So most of these short answer questions are just algebraic manipulation. So one thing that you will need to know is that resistance is the resistivity times the length divided by the area. Okay, so that's not too bad. We also have several definitions of power, but one of them is that it's the voltage squared over the resistance. It's also the current times the voltage, or the current squared times the resistance. Those are all the same. So we can calculate all of these quantities at some temperature. So here this question asks us to do it at 20 degrees Celsius. And then we can find all of the same quantities at a larger temperature by using the fact that resistance and resistivity, both of them have the same form of temperature dependence, obey this equation. So the resistance at some temperature is the resistance at some reference temperature times 1 plus alpha times the change in the temperature. So in this case, going from 40 degrees to 20 degrees, or from 20 degrees to 40 degrees, that's a change of 20 degrees. So that's what would go here. And then alpha was given, and we found this resistance at 20 degrees using this formula. Okay. Yeah, and so this is also just straightforward using this equation, that our drift speed is our current divided by the density of charge carriers. For most metals, this will be the density of electrons. So that's what's given here. It's how many electrons there are in each cubic meter times the charge of each charge carrier. So most of the time, this will be the charge of an electron, 1.6 times 10 to the minus 19. Now, the only tricky part is we use the positive version if we're looking for just drift speed. If we were looking for drift velocity, then the sign matters. But just for speed, it doesn't matter. Then we also divide by the cross-sectional area. Okay. Now we didn't know the current here. We could have found it. We had all the information in the previous problem necessary. Or we could just replace the current with V over R. Ohm's law tells us that that's what we can do. So that's what I did here. All right, chapter 10. So this one also is mostly an easy chapter. The only tricky part are RC circuits. So we'll get to that in a second. So an ideal battery has a terminal voltage equal to its EMF. That's true. Only in a non-ideal battery are these things not equal. And the reason why is because a non-ideal battery has some inherent amount of resistance in it. There's something that opposes electricity flowing in it. Now, the vast majority of the time, we just assume that they're ideal. Yeah, I mean, I won't ask you a question about like an actual math question about a non-ideal battery. I just need you to know that. Okay, an EMF does stand for electromotive force, but it has nothing to do with a force. This is just a historical anachronism, essentially. They initially named it this because they thought it was a force, but it's not. Really, it's just a voltage. So essentially just another name for voltage. All right, resistors in parallel have an equivalent resistance smaller than any of the resistances of the individual resistors. This is true. It works exactly the opposite of the way that capacitors do. So resistors in parallel, the equivalent resistance is smaller than any of the individual resistances. And for resistors in series, the equivalent resistance is larger than any of the individual ones. Okay. Kirchhoff's loop rule, remember, tells us that the sum of the voltages around a closed loop has to be zero. That is telling us the exact same thing as conservation of energy. That's because as electrons flow around a closed loop, they don't gain more and more energy. Remember, energy is related to voltage. So any energy that they gain has to be lost, which also means any voltage that they gain has to be lost as well. All right, similarly, Kirchhoff's junction rule, remember that says that the sum of the currents going into a junction has to equal the sum of the currents leaving. That's saying the same thing as conservation of charge. Just means that charge can't be created out of nothing and charge can't go in somewhere and then just disappear. Charges can't be created or destroyed. Okay. So if a capacitor is in series with a battery, this is an RC circuit, remember, because it also has a resistor. It's true, it takes an infinite amount of time for it to become fully charged. So if you remember, it has this 1 minus e to something kind of thing. That's the form of it. And so only as t goes to infinity does the exponential go to 0 and you're maximally charged. So similarly, if a capacitor is discharging, if it's discharging, that means there's no battery. It only has a capacitor and a resistor. Then the voltage will decrease with time, but it also has this exponential behavior where it takes an infinite amount of time to actually reach 0. All right, so one more. Resistors in parallel always have the same magnitude of voltage across them. Yes. So just like the capacitors that we saw before, if they're in parallel, that means there's a loop, a closed loop that only goes through each resistor. And so the sum of those voltages have to be 0, which means if we only care about the voltage and not its sign, they have to have the same voltage. I lied one more. Resistors in series have to have the same current going through them. That's because if there's in series, that means there's no junction between them. So any current that goes through one resistor also has to go through the other one. Okay, short answer questions. A capacitor of this capacitance is connected in series with a 10-volt battery and a 150 ohm resistor. And the circuit is connected at t equals 0. At what time will the current reach 60 milliamps? Okay, so this is just using the equations that we have here. We know for a charging capacitor, which is what this is because it's in series with a battery, that the current has this form. It's the EMF of the battery divided by the resistance times e to the minus time over the resistance times the capacitance. And so we just set the current equal to this thing, and then we solve for time. So I'm sure all of you are familiar with that. You just get rid of the e by taking a natural log like I've done here. And then we know all of these quantities, we can plug them in, and that gives us the time. Now it also asks what percentage is this current of the maximum current. So I just take our 0.6 divided by the maximum current, and the maximum current is this thing. So it is the EMF of the battery divided by the resistance. So if you divide these, you get 0.9, and 0.9 is of course 90%. All right, now suppose the capacitor is removed from the circuit, this circuit described here, and placed in a different circuit that only has a resistor and no battery. Okay, so we want to know what is the voltage across the resistor, and then what is the charge on each plate. So the voltage across the resistor is always the current times the resistance. This is just Ohm's law, so this is true. So I know how to find the current as a function of time. This is a discharging capacitor, and so the current looks like this. There's actually a minus sign here, but we don't care about the sign, so I just took the absolute value. Okay. Now our V naught here is how charged the capacitor was initially. So whenever it's charging, it only depends on the EMF of the battery and the resistance of the resistor. But when it's discharging, it depends on how charged it was initially. So what the initial voltage was across the capacitor and the initial charge. So to find this, I need to go back up and use the equation for a charging capacitor, which is this thing, and then plug in the time at which it was disconnected. So we had it in this one circuit and it was charging. Then we took it out of that circuit. So it has some voltage and some charge, and we put it in a different circuit. So we have to find the initial voltage here, which means we have to use the charging equation. So voltage is the EMF of the battery times this 1 minus E thing. Now I know the time at which it was removed. I know the resistance and the capacitance. So I can just plug these things in and find what the initial voltage is. Okay. Well, remember, the only reason why we needed that was to find the current in our discharging capacitor system at 1.5 seconds. So this is the equation for the current. I just plug in 1.5 seconds here, and all these other quantities were given in the problem except for V naught, which we just found. And so that gives us the current at this time. What we actually asked for was the voltage across the resistor. Voltage across the resistor is the current times the resistance. So here's our current. Our resistance was given, so we can find the voltage here. Now it also asks us what is the charge on each plate. Well, for a discharging capacitor, the charge has this form. It's however much it was initially charged times this exponential. So once again, we have to find how charged it was initially. So we'll have to go back up to this first problem here, use the equation for a charging capacitor, and solve for the charge at the time at which it was disconnected, which we saw was 0.0049 seconds. So this is the equation for a charging capacitor. We know the capacitance, we know the EMF of the battery, we know the time, the resistance, and the capacitance. So we can solve for how charged it was initially. And then we can plug that back into this equation and find the charge on each plate. Okay. Now, we can have combination circuits with resistors, just like we could with capacitors. And essentially, we work them the exact same way. We look at some subset of the circuit where all the resistors are in parallel or all of them are in series. We replace them with an equivalent one, and then we do the same thing over again. So here we can notice that R2, R3, and R4 are all in parallel, which means that we can replace them with a single resistor, R2, 3, 4. And resistors in parallel have this form. We add the inverses and take the inverse to find the equivalent resistance. And so just like before, now I redraw the circuit here, but instead of having all of these, I replace them with just one. And I don't want to leave any part of the circuit bare with nothing across it at all. So the only way to redraw it is like this, by replacing all three of those with one and not leaving any section of wire between a junction just empty. Okay, so now I only have these four resistors left and they're all in series, right? All of the current that goes through this one has to go through this one, has to go through this one, and has to go through this one, because there's nowhere else for the current to go and the charges can't be created or destroyed. So we can replace all of these with a single resistor, which I'll call REQ. For resistors in series, you just add all their individual resistances together. So we can redraw the circuit one more time, and we just have the battery in this one resistor now. Now the question also asks to find the current and the voltage across each resistor. All right, well, I do the same thing here that I was doing with capacitors before. We start with the simplest circuit after we replaced all the resistors with a single one. And we can find the voltage straight away, right? This is a closed loop, so this voltage has to be the same as this voltage. And so the voltage across our equivalent resistance is 12 volts. Now I can find the current with Ohm's law. Current is V over R. So the current through this resistor is its voltage divided by its resistance. It's given by this number here. Okay, but I don't really care about that. That's not what the question asks. The question asks for the current and the voltage through all of these resistors. But now that I know it through the equivalent resistor, I can work backward and find it from the others. So we constructed REQ from R1, R2, 3, 4, R5, and I6 and R6, and they were all in series. Because they're in series, that means they have to have the same current, because there's nowhere else for the current to go. And that current has to be the same as the equivalent current. So I haven't done any work yet, and I already know the current through all of these resistors. And then I can use Ohm's law to find the voltage. The voltage is always the current times the resistance. So I can find the voltage across all of these. And anytime you're doing resistors in series, you can check and make sure that you're right. If you add up all of their voltages, you should get the voltage across the equivalent resistor. So the REQ that we started with, we said it had 12 volts across it. And if we add all of these voltages together, sorry, 1, 2, 4. If you add all of these voltages together, you get 12 volts. Okay, so I know the current and the voltage through R1, R5, R6, and this R2, 3, 4. I don't care about R2, 3, 4. I care about R2, R3, and R4. R2, 3, 4 came from these R2, R3, and R4, and they were in parallel. Now, as I said several times now, if they're in parallel, it means they have to have the same voltage, and they have to have the same voltage as the equivalent resistor. So all of these voltages are equal, and they have to equal the voltage across R2, 3, 4. And then I can find the currents using Ohm's law. So for in each case, the current is the voltage divided by the resistance. I'll get different values for each of these. And once again, I can check to see if I'm right. Anytime you have resistors in parallel, you can add all of the currents together, and you should get the current through the equivalent resistor. So here, when we added I2, I3, and I4 together, we got 0.0629 amps, which was very close to the current through R2, 3, 4, 0.0628. So it's off because we rounded something somewhere, but very close. Okay. Now for the problem you guys have all been dreading, the Kirchhoff problem. So if we have a circuit like this, these resistors are in series or in parallel with any of the other ones. I mean, these are in series, but they're not in series or in parallel with this one. These two are not in parallel. It's because of the presence of these batteries here. They sort of mess everything up. So the only way to solve this circuit is to use Kirchhoff's rules. So the first thing we should do if we're doing a Kirchhoff problem is draw the current through each part of the circuit, give it a direction, and give it a name. Now the direction doesn't matter You're just guessing. In the end, you might be wrong. It does not matter at all. So through this part of the circuit, I'll call that I1, and I'll assume that it goes this way. So once again, this is a choice. I could have picked the other direction. It doesn't matter. Now here we get to a junction, which means that the current has to split apart. So I'll say I2 goes through this part and I3 goes through this part. Just like before, these directions are arbitrary. They could be coming the other way, or just one of them could be coming the other way, whatever. Okay. Now I'm supposed to write a series of equations that govern these. So I can use the junction rule right away because I've already drawn these currents here. So at this point, this is a junction in a circuit. We have I1 coming in and I2 and I3 leaving. So that tells me that I has to be equal to I2 plus I3, or I1 has to be I2 plus I3. Now we have a second junction here, but it tells us all the same information. So here we have I2 and I3 coming in and I1 leaving. So I2 plus I3 has to be equal to I1. That's the same equation that we had before. So the junction rule gives us this equation. Okay. And so we have three unknowns. We don't know I1, we don't know I2, and we don't know I3. So we have three unknowns, which means that we'll need two more equations to solve this. Okay. So that means I have to pick out two loops. Now in our circuit up here, we actually have three loops here, right? We have this bigger loop that goes like this around this side. We have this small loop. And then we also have this big loop that goes around the bottom here. So we only need two of these loops, and you're free to pick any two that you want to. You're going to get the same answer regardless. So the way I've drawn it here, I chose this big loop where I go around the top part, and I go around it this way. And then I also chose the little loop where I go around it this way. Okay. So to use the loop rule to actually construct an equation, you have to know if you go across a battery, if you go from negative to positive, you get a positive voltage. If you go from positive to negative, you get a negative voltage. And when it comes to resistors, if you go with the current, then you have a voltage drop. And if you go against the current, then you have a voltage gain. So let's do this big loop first. We can start anywhere we want. Let's go around the same direction as the current, like I said down there. Let's start with our battery here, and we're going this way. So as we go across this battery, we're going from negative to positive. So we have positive the EMF of this battery. When we get to this resistor, we're going in the same direction as the current. So we have a voltage drop, and that voltage drop is I1 times this resistance. So we know that just from Ohm's law. When we get to this resistor, we're still going with the current. So we have another voltage drop of I1 times this resistance. Okay, now there's no more components here, so I go up here. Next, I go across this battery. Once again, I'm going from negative to positive, so I have positive the EMF of our battery here. And then I hit this resistor. I'm going with the current. So this time it's I2, because this is the current that's going through this resistor times its resistance. Okay, so I keep going. And then finally I hit this last component, which is my last resistor. And it has I1 going through it. So we have a voltage drop of I1 times its resistance. Okay, so that's exactly this equation that I've written here. Yeah, so it's in a different order. I guess I started here, but it's all the same stuff. So when you add all of these voltages together, because it's a closed loop, it has to be equal to 0. So I've sort of cut off the 0 here, but there should be a 0 over here. All of these things have to add together to be 0. All right, now we can do the same thing with our smaller loop, and that gives us this equation. So we have 3 equations here and 3 unknowns. So we have all of the information that we need to solve for I1, I2, and I3. All right, now the next step is to actually plug our numbers in. So instead of just calling this epsilon 2, R4, or whatever, We know the R's, we know all of the resistances, they were given in the problem. And we know all of the EMFs of our batteries, they were also given in the problem. So when we plug all those in, we get this stuff. So now we have 3 equations and 3 unknowns. Okay. And so your next step is going to be somehow to reduce it to 2 equations and 2 unknowns. And if we have this set up, that's pretty easy. So our first equation, or I guess equation 2 actually, is only a function of I1 and I2, while our equation 3 is only a function of I3 and I2. So if we could somehow replace I3 with some function of I1 and I2, then we would have 2 equations and 2 unknowns. So that's exactly what I did here. If we rearrange this first equation, or I3 is I1 minus I2, we can replace I3 here in equation 3 with I1 minus I2 then. And so that leaves us with these 2 equations. One of them is just equation 2 written again, and the other one is this equation with I3 replaced by this. So now we have 2 equations and 2 unknowns. We could solve either via substitution or elimination. In this case, substitution is slightly easier. So the way I did it was I solved for I1 in equation B as a function of I2. And then you just plug that into the other equation, and that will give you a function only of I2. So you can solve for I2. Then you can plug that back in up here to find I1. And then you can plug that back into our equation 1 that we had written up there to find I3. Okay, so this is the actual answer. These are the currents in each part of the circuit here. Now, one thing to note is that I3, we found a negative number. So what does that mean? That means all the way up here, when we guessed the directions of the current, we just guessed wrong for I3. Instead of going this way, it actually goes the other way. So it doesn't matter what direction you guess. If you're wrong, you'll just get a negative number in the end. Okay. So we wrote the series of equations, we solved them. The only last thing we have to do is solve for VPA. So I drew that again down here. We need to know the voltage between these 2 points. Okay. And we drew I2 going this way. That'll be important. So VBA is the voltage from A to B. So we just use the rules that we used before to solve for the voltage between these 2 points. So we have 2 components here. We have a resistor and we have a battery. So going from A to B, we travel across this resistor in the opposite direction of the current, which means that we have a voltage gain of the resistance times the current. When we get to the battery, we're going from the positive side to the negative side, which means that we have a voltage drop of the EMF of our battery, which is 15 volts in this case. So we solve for I2 up there. We just plug in our number for I2. We find that this is the voltage between these 2 points. So we could do the same thing anywhere that we want to in the circuit. Could be between this point and this point. And that, in which case we have 3 different components. You have this resistor, this battery, and this resistor. And you could do it with as many different places as you want. Okay, so that's it for this chapter. One more chapter, chapter 11, magnetic forces and fields. Okay, so the first question says an electron is traveling down in Earth's magnetic field, which has a component that points down and another that points north. The component pointing down doesn't matter. Only the part of the magnetic field that's perpendicular to the velocity matters. Okay. All right, now the magnetic force on the electron described above points west. All right, so this is an electron, which means that we use our left hand. The part of the magnetic field pointing down doesn't matter. So we put our fingers in the direction of the velocity. So that's down. And then we curl them in the direction of the magnetic field, which was north. So if you're doing this, hopefully you're doing this with me, your thumb is pointing in the direction of west. So fingers go down, we curl them in the direction of north. We're using our left hand, so our thumb points west. Okay, now charged particles moving in magnetic fields have three possible trajectories, at least if the magnetic force is the only force. There's linear. This occurs if the velocity is either parallel or anti-parallel with the magnetic field. Remember, magnetic fields only affect particles with velocities that are perpendicular to the magnetic field. So if it's moving with or exactly against the magnetic field, there's no effect at all, and it just keeps moving in a straight line. Now, if the velocity is perpendicular to the magnetic field, then it just goes around and around and around in a circle. So that's a circular trajectory. Now, if it has a velocity that's partially along the magnetic field and partially perpendicular, well, the part that's along the magnetic field will be unaffected. It'll just keep moving while it makes a circle in the other direction. So if it makes a circle in one direction while it's going straight in the other, that's a helical or spiral trajectory. Okay. The magnetic force is maximized when the velocity is perpendicular to the magnetic field. Just talked about that. And as far as we know, there are no magnetic monopoles. Remember, you can't have a north pole without a south pole or a south pole without a north pole. So mono means one. We can't have just one of those. So there are no magnetic monopoles. Once again, at least as far as we know, maybe they exist somewhere. All right. So this is just talking about the right-hand rule. To find the direction of the magnetic force on a current carrying wire, you point your fingers in the direction of the current and then curl them in the direction of the magnetic field. You do that with your right hand, and then your thumb points in the direction of the force. All right, an electric motor consists of a current carrying loop of wire in a magnetic field. Although there is no net force, there is a net torque. This is true. That's what we did in class today. All right, a single loop of wire, regardless of its shape, has the magnetic dipole moment given by the current times the area in the normal direction. That's true. Remember, this normal direction is given by the second right-hand rule. Okay, long answers. An electron is traveling north in a constant magnetic field which points up. Draw the trajectory the electron makes in a labeled coordinate system. All right, so I label my coordinate system here. I let this direction be north and up be out of the page because that's the only way to draw the circle. So if our electron is traveling north in a magnetic, so that's up as I've drawn it on the page, the magnetic field is pointing up, which is out of the page as I've drawn it here. Then if you use your left hand, since it's an electron, you point your fingers in the direction of the velocity, curl them in the direction of the magnetic field. You'll see that your thumb points to the left, which is west in this coordinate system. And since the velocity is perpendicular to the magnetic field, it makes a circle. So the circle goes around like this. And we can describe this trajectory with two quantities, the radius, which is given by this thing, and our period, which is given by this thing. So alternatively, we could have also used the frequency, which is 1 over the period, whatever, same thing. So the radius is explanatory. The period, remember, is the amount of time that it takes for the electron to make one full revolution. In other words, to come back to where it started. Okay, so the next question, a 55 centimeter section of wires carrying 2.7 amps traveling north and is suspended in midair. Now, this section of wires in a constant magnetic field of 1.5 Tesla that points 30 degrees west of south. So our current is running north. Let's use the same coordinate system that we had here. So that's up on the page. The current is running in this way, and our magnetic field is 30 degrees west of south. So here's south, here's west. It's 30 degrees out like this. So I've drawn our magnetic field here. Now our magnetic force is ILB times sine of theta, where theta is the angle between the current and the magnetic field. So that's not this 30 degrees down here. It's this 150 degrees, because this is the direction of the current, this is the direction of the magnetic field. Okay, now because it's suspended in midair, that means that this force exactly counters the force of gravity. So we can divide by the acceleration due to gravity and find the mass. So we know all these quantities now. So if you plug numbers in, this is what you get for the mass. Okay, So a charge has this velocity and it has this magnetic field. Well, we did this today. We know how to take this cross product. We write the matrix down that has elements of I hat, j hat, and k hat. Then it has the elements of the velocity, the I hat part, the j hat part, and the k hat part. And the third row has the components of the magnetic field. And then we just find the determinant using whatever method you like. You can use the method that we did today where we draw multiple copies of the matrix, or if you want to use the subdeterminants or whatever they call it, that's fine too. Okay, so a tightly wrapped circular loops of wire has a radius of this and a current of this. The current is in the direction here. What is the magnetic dipole moment? Okay, well, here I've drawn a coordinate system. So this is X, this is Y, and out of the page is Z. And remember, to find the direction of the magnetic dipole moment, we use the second right-hand rule. So we take our right hand, we curl our fingers in the direction of the current, which means we curl them around like this. If you curl your fingers in this direction, then your thumb is sticking out towards you. That's the direction of this magnetic dipole moment. So in this coordinate system, this is in the positive Z direction. It's out of the page. And it has a value of the number of loops times the current times the area. So it's a circle, we have the radius, we can find the area. There are 12 loops and we were given the current. So we just multiply those things together. And our magnetic dipole moment is this number. Remember, it's measured in amps times meters squared. And it's in the positive Z or the K hat direction. All right, so next we're asked to find, okay, so this loop is in an external magnetic field that has some angle of 37 degrees relative to the dipole moment. And we want to find the torque and the potential energy. All right, well, the magnitude of our torque, the torque itself is the dipole moment crossed with the magnetic field. But if we only want the magnitude, that's the magnitude of mu times the magnitude of B times sine of the angle between them. And we know everything, right? We know the magnitude of this vector. It's just this number here. We were given the magnetic field and we were also given the angle. We just plug those things in and we get this number. The torque is measured in Newton meters. And we can also find the potential energy here. It's given by minus the dipole moment dotted into the magnetic field, or that's the exact same thing as the magnitude of the dipole moment times the magnitude of the magnetic field times cosine of the angle between them. Don't forget the minus sign. So that gives us this thing. Energy is measured in joules. Okay, one more? Is this two more? All right. So we have this rectangular circuit here that's inside of this magnetic field. And we want to know what is the net force. Okay. Well, first off, this wire has no net force on it at all because it's parallel to the magnetic field. Similarly, this wire has no force on it at all because it's anti-parallel with the magnetic field. These two do have forces on them though. The force is given by I, the current, times the length, times the magnetic field, times sine of the angle between them. We can see here, these are at right angles, right? This one's going up while our magnetic field is going right. That's an angle of 90 degrees. So the force is just I times the length times the magnetic field. Well, the length of this wire is S2. The magnetic field is B and the current is I. So our force 1 here is I S2 times B. And everything is exactly the same about the wire on this side. Okay, so those are the magnitudes of our forces. Now what we need to find is the direction. We can use the right-hand rule to do this. Let's do this side first. We put our fingers in the direction of the current. So we put our fingers like this. We curl them in the direction of the magnetic field. That means your fingers should point to the right and your thumb should be pointing down. So the force on this one is down. If we do the same thing for this one, we put our fingers down along this direction and curl them in the direction of the magnetic field. So fingers down, we curl to the right, your thumb is pointing out. So that's the direction of the force here. So our forces have the same magnitude, but opposite directions, which means that our net force is 0. Okay. All right. Now we're asked to find torque. Well, we sort of already did this part. We said only these two have forces on them, which means those are also the only sides that have torques. Okay. Torque is usually given by R, which remember is the distance to the axis of rotation, F, which is the force that's causing the torque, times sine of the angle between them. But we can see if we drew this sideways like we did in class today, I guess I can do it. If we draw this sideways from this view, we have, which direction was it? We have F1 that's going down here. And we have F2 that's going up here. Now this thing is going to rotate about some point in the middle here. It's going to rotate about that. And so our vector that points from the axis of rotation to our force is this vector. So this is R1. And starting from the same point, this is R2. Now this whole thing had a length of S1. So this has a length of S1 over 2, and so does this one. Okay, let's switch back to black. So our torque, our magnitude of torque, at least caused by F1, is this distance times this force times sine of the angle between them. But we can see these vectors are perpendicular, right? This vector is moving to the left and this vector is moving down. So it's just R times F. So that's S1 over 2 times F1. And our torque 2 is going to be exactly the same. It's S1 over 2 times F2. Okay. And these torques also point in the same direction. Right? If we ignore this first force over here and just look at force 2, that's going to cause this thing to rotate around like this. And if we ignore F2 and just look at F1, that'll also cause this thing to rotate around like this. So the torques are in the same direction. We can just add them together. Yeah, so they're both R1 times F1 and then R2 times F2, but R1 and R2 are both S1 over 2. So they both have this form. It's S1 over 2 times the force, and the force we saw above was the current times S2 times B. Torque 2 is the same. So when we add these together, we get the current times S1 times S2 times B. This is a rectangle that has side lengths S1 and S2. So if we multiply these things together, we just get the area that's inside of this, that's sort of perimetered by this circuit here. So this is the torque. Now note, this is exactly what we would have gotten if we took the cross product between mu and the magnetic field, if we first found the magnetic dipole moment. But this question asks us to find it just from the force. Okay, so that's everything that's on your test. I hope you guys do well.